Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss temperature entropy diagrams for Carnot's cycle. Let's begin. In previous videos, we see the PV diagram for Carnot's cycle, how TS diagram means temperature entropy diagram is very similar to that of pressure volume diagram for Carnot's reversible heat engine. So we know Carnot's reversible cycle consists of 4 steps. There are 2 isothermals and 2 adiabatics. In 2 isothermals, one is isothermal expansion and another one is isothermal compression, and in case of adiabatics, 2 adiabatics, one is adiabatic compression and another one is adiabatic expansion. So in step 1, let I take isothermal expansion. Isothermal expansion. What happened in case of isothermal expansion? The working substance absorbs Q1 amount of heat from the source at temperature T1. Here the working substance absorbs Q1 amount of heat from the source at temperature T1. Hence, the entropy of the working substance increases. Therefore, entropy of working substance increases. Let the entropy of working substance increases, that entropy from S1 to S2, and this process is represented by the horizontal line AB, which is parallel to the axis S and T. So I draw the graph here. Here S in x axis and temperature in y axis. Let that is from S1, S2, T2, T1, and the isothermal expansion line be AB, which is parallel to that of x axis. That line segment represent isothermal expansion, here AB, which represents isothermal expansion. Isothermal expansion, and that is step 1. Here is the step 1. Okay. What happened to that of step 1? Since dq is equal to T ds. Therefore Q1 is equal to T1, the change in entropy, that is S2 minus S1, S2 minus S1, that is the area of, if I draw the line here, the area inscribed in between the points are E, F. So the area of A, B, F, E, A, that is area under this, that is the amount of Q1. Next, step 2. What happened in step 2? In step 2, which is adiabatic expansion, which is adiabatic expansion. What happened in that of adiabatic expansion? The temperature of working substance decreases from T1 to T2, and the working substance does not lose or gain heat from that of source or sink. Hence the entropy remains constant. Here temperature of working substance decreases from T1 to T2, and the working substance does not gain or lose heat from the source or sink. That's why the entropy remains constant. Hence entropy remains constant, and that process, that is adiabatic expansion, which is represented by the vertical line BC. That is the vertical line BC, which show the adiabatic expansion, which is at step 2. Step 2, which is vertical line BC, that is the vertical line BC that represent the adiabatic expansion. Here is the horizontal line AB. Now step number 3. Step number 3, which is isothermal compression, isothermal compression, what happened or how we represent in graph of temperature and entropy. So in isothermal compression, that is step number 3, what happened, the working substance loses the amount of heat Q2 to the sink at temperature T2. So here the working substance loses heat Q2 to the sink at temperature T2, hence the entropy will be decreases, hence entropy of working substance decreases from S2 to S1, and in graph it is represented by the horizontal line CD. So let's draw that graph here. The horizontal line, that is T2 here. So this portion, that is C D, and it is known as isothermal compression. Isothermal compression, that is step number 3. In this case, what should be the heat? In this case, Q2, here Q2 will be T2 S2 minus S1, that represent in the graph the area under DCFED, that area is the amount of heat Q2, that the area of CDEFC. CDFEC, that is the area under that portion. Now step number 4, that is the final step, which is adiabatic compression. Step number 4, which is adiabatic compression. What happened in that of adiabatic compression? No heat enters or leave that of working substance, hence the entropy remains constant. Here no heat enters or absorbs, enters or leave, we can say that is the leave. No heat enters or leave to the working substance, that's why the entropy remains constant, hence entropy remains constant. Since entropy remains constant and temperature changes from, or that increases from T2 to T1, and this process is represented by the vertical line dA. Vertical line dA, represents that particular process, that is adiabatic compression. Let I take here the vertical line dA, that is adiabatic compression. Adiabatic compression, here is the step number 4. Step number 4, that is the range of temperature T1 and T2, that is the range of entropy S1 and S2. And the region means the region A, B, C, D, that represent the triangle A, B, C, D, which represent what? That is the TS diagram of Carnot cycle, that represents the TS diagram of Carnot cycle. TS diagram of Carnot's cycle, that is temperature and entropy diagram of Carnot's cycle. Now we have to calculate the efficiency of that Carnot cycle by using that particular TS diagram. So let us evaluate what should be the efficiency. Therefore, to calculate the efficiency, first we take what should be the net amount of heat that converted into work. So the net heat converted into work during one complete Carnot cycle. Carnot cycle is given by, that is Q1 minus Q2, that is Q1 minus Q2. Now what should be the value of Q1 minus Q2? Therefore Q1 minus Q2 be the area under that rectangle A, B, C, D. So how we get the area under that particular rectangle? Now we subtract the area under A, B, F, E to the area under that small area C, D, E, F. When we subtract that area to this area, then we find the area under that rectangle A, B, C, D. So I write here what should be the Q1 minus Q2, which is known as the net heat that converted into work done during a particular single cycle of Carnot's heat engine. That is the area of A, B, F, E, A minus area of C, D, E, F, C, or that is Q1 minus Q2 will be the area under area of A, B, C, D, that is the shaded region, Now the efficiency of Carnot's heat engine, efficiency of Carnot's heat engine is given by eta, that is the heat energy converted into work divided by how much heat is absorbed. So heat energy converted into work to how much amount of heat is absorbed, that is the total heat absorbed converted into work, what amount, that is Q1 minus Q2, that is Q1 minus Q2, amount of heat absorbed, that is Q1. In place of Q1 I substitute, that is T1 will into S2 minus S1, that is T1 S2 minus S1 minus, in place of Q2 I substitute the value here, that is T2 S2 minus S1, here T2 S2 minus S1 divided by, in place of Q1 same thing, that is T1 S2 minus S1. Here in numerator we take common as S2 minus S1, there will be T1 minus T2 common as S2 minus S1 divided by T1 S2 minus S1, S2 minus S1, S2 minus S1 cancel out here, that is T1 divided by T1 minus T2 divided by T1, that is 1 minus T2 by T1, or eta is equal to 1 minus T2 by T1. Look at that particular expression. That type of expression we get in case of PV diagram to get the efficiency of Carnot's heat engine. So this is the expression of, this is the expression of eta, that is the efficiency of Carnot's heat engine, which is same on PV diagram. In this way we relate TS diagram, that is temperature entropy diagram for Carnot cycle, is very similar to that of PV diagram, pressure volume diagram of Carnot cycle. In both the cases we calculate the efficiency of Carnot heat engine. So with the help of this video lecture we understand what is temperature entropy diagrams for Carnot cycle, that is TS diagram. We take the reversible Carnot heat engine, and this is the diagrammatically view of that particular portion. 4 steps, each step what should be the entropy here, and finally we calculate the entropy by using this TS diagram of Carnot's heat engine, which is very similar to that of PV diagram. So with this useful and informative notes, let me wind up this session. Thank you.